Hello and welcome to my channel. My name is Sergey. I'm building robots and I'm here to share my experience so far. After a short demo, I'll describe in brief which skills you need to master in order to build your own robot. Main idea of this video is to give basic understanding of the process and to warn about common pitfalls, which can cost you extra money and a lot of time wasted. I won't show you the best practice, but I've tried to gather here all the information that I was lacking when I started. A little introduction why my robot looks like this. After creating my first robot, I've decided to create something recognizable from a video game or a movie. Also, it was an interesting experiment whether a fictional character would be able to move in real life. Would it be efficient enough? And as long as I was a fan of Blizzard games, I've chosen Fenix, specifically its model from Heroes of the Storm. My first attempts of creating the design on my own were not successful, but luckily I came across the model made by Alex on ArtStation, and he agreed to send me the sources. Next challenge was to adapt the model for all the servo motors and electronics. I couldn't make the original joints, I'd need to use brushless motors with planetary or cycloidal gearboxes for this, but this technology is at this moment beyond my skills, so I've ended up using standard servos. But the remaining parts of the robot almost exactly match the model, and in general it looks like its prototype. So let's move on to the demonstration. Robot can be controlled via DualShock joystick or web interface. Commands are the same, I'll show them on joystick. It has 4 modes. Sentry mode means that it remains stationary and can look around. This mode is made mainly to test its limits in moving body to the sides, up and down. Battle mode gives it the ability to hit something with his front legs. Walking mode allows it to move one leg at a time. You can see that robot shifts its center of mass to get each leg off the ground and move it to the next position. It's slow but precise. This mode is used for overcoming obstacles. Though this particular model has too many constraints in its joints, so I won't be showing any rugged terrain movement today. Running mode allows it to move 2 legs at the same time, resulting in much greater overall speed. When switching to this mode, it moves legs closer to the center to lower the length of its levers. And though this mode is called running, it is still slow, but it is the best speed I could achieve with this design and these servo motors. It has got powerful LEDs, so it can navigate in the dark. And here is how it looks like from a first-person view. It transfers video stream to a virtual machine in the cloud. Delay is around 1/10 of a second. For more effective movement, I've had to replace original pointer toes with star toes. Now let's go step by step through the process of creation of a robot. It consists of 8 parts. CPU, the computer which controls everything. Motors, servo or DC motors that will make your robot move. Power supply, brain and motors gonna need energy to work. Code, the program that will tell your robot how to move. Controls, some way to control the movement of your robot. Shell, the body. Sensors and periphery, and optional printed circuit board to make it look neater. Let's start with the CPU. You can use any small computer of your choice. Most popular options are Arduino and Raspberry Pi. They've got many cheaper analogs. Most projects I've seen are based on Arduino. It is cheaper and easier to start working with. But in my opinion, for more complex projects you'd prefer a more powerful computer. That's why I'm working with Raspberry Pi. It is streaming video, reading joystick commands and running several Python scripts in parallel, and it was really easy to implement. My first robot was on Arduino and I struggled a lot with implementing some things, but maybe I'm just not smart enough. You can always choose some cheaper option, but then you will have to spend much more time optimizing your code and writing integration with all the required sensors. There is no good or bad option, just choose whatever fits your needs better, but main rule is as follows. If you want to spend less money on the computer, you will have to spend more time writing code, and vice versa. Next, you've got to choose motors for the joints. They fall into two major categories. Classic servo motors that can be controlled directly from your computer pins via PWM, which stands for Pulse Width Modulation, or any other protocol like UART. Servos can hold particular position, more expensive ones offer more precision, some have feedback. Direct current motors, strong ones, are usually brushless, so they are called BLDC motors. With low kV can also be used, but they are more difficult to work with. They need separate controllers or drivers. You need to add speed reducers like pulleys with belts, planetary or cycloidal gearboxes or some sort of worm gear. All this makes joints bigger and heavier. Also, you're gonna need an angle sensor to understand the current position of your motor, because they can only change rotation speed or direction and can't hold a particular angle. You've got to implement this part yourself. For a small hobby robot, servos are the go-to option, especially if you don't have much experience. They are really easy to work with. Some of them also provide servo brackets that make them easy to be installed, and when they no longer satisfy your needs, you can move further and switch to BLDC motors. I'm using Leventhal LX16A because they have feedback. It is very important if you want precise movements. But extra features come at a price of complexity. I can't control them directly via PWM and have to use their proprietary board over UART protocol. The downside effect of it is that it is harder to debug. For example, on high speeds, servers start missing some messages and I have to resend them. I can't find the cause of this problem because their control board for me is like a black box. Now let's talk about power supply. This is a vast topic, I'll try to make it as short as possible. Here are three variables that you need to keep in mind: voltage, amperage, capacity. First, you need to understand how much voltage you need for servos and microcontroller to work. Most servos work at 5 to 8 volts, you can check it in the datasheet, and their torque goes down when the voltage drops. Large servos or BLDC motors may require up to 24 volts or even more. I won't be describing this schema as long as I haven't built it myself yet. Most microcontrollers work at 5 volts. Also in the datasheet you can find the required amperage. For example, my servos can use up to 3 amperes, 16 servos, so theoretical maximum current should be 48 amperes. Practically, your servos cannot be fully loaded all at the same time, so 20 amperes should be more than enough for peaks, with average consumption around 3 to 8 amperes. And the last part, capacity. How long you want your robot to work? Let's suppose your robot consumes 6 amperes per second in average. So if you take batteries with 3 ampere hours, it is going to work for 30 minutes. That's all like ideal conditions and not accurate assumptions. There are hundreds of nuances. I am not good at physics to describe them all. For example, voltage drops on the batteries when they are getting depleted. Also you lose energy on the DC to DC down converter. Real battery's capacity differs from theoretical and so on. I'd suggest you divide the calculated number by 2 to not get disappointed. So we end up with 15 minutes for this example. Though this is an assumption for a non-stop running, you won't be using your robot like this because servos may get overheated and burned down. While holding position, servos consume around 1/10 to 1/5 of the running amperage. So with normal usage scenario, your robot will live for 30 to 45 minutes on this kind of battery. If you want your robot to work for more than an hour, you've got to put 2 batteries of required voltage in parallel. I'm using 18650 batteries in a mode known as 2S2P, which stands for 2 in series, 2 in parallel. With maximum charge they provide 8.4 volts. As they get depleted, voltage drops to 6 volts. Each battery's claimed amperage is 20 amperes and capacity 3 ampere hour. and as we have them two in parallel, theoretical amperage and capacity are doubled. Initial voltage is good for servos to work, but microcontroller requires 5 volts, so we need a DC to DC down converter. You've got to choose a converter depending on your needs. Don't forget to check its maximum current output. Also, don't forget that it is recommended to use different power sources for your motors and microcontrollers, or peaks may reset the latter. If the power supply is shared between them, capacitors and stabilizers are required. Both Raspberry Pi and converter already have them on board. If batteries give enough current, our controller is safe. If you want batteries to be charged in place, you've got to make schema more complex. Add a BMS, battery management system, another DC to DC down, and an adapter. I've got a 12 volts 3 amperes adapter. Converter lowers voltage and stabilizes it, and BMS helps them to not get overcharged or fully depleted, and protects against short circuit. If you want another setup like 3S2P or 2S4P, you can easily find them in the internet. Now let's discuss the code. The main notion that you've got to understand is inverse kinematics. It allows you to calculate leg angles required to put the end of robot's leg to its desired position. There are tons of videos on this topic. I won't explain it here, it's school math. I'd recommend you to find the algorithm on your own as an exercise, but still I'll leave a link to my code in the description. Though basic version assumes that you have 2 joints and exactly 1 decision, but in my case I have 3 joints in each legs. So inverse kinematics becomes more complex and there is an infinite amount of decisions to achieve the same point. To make this work, I evaluate tens of different options and choose the best decision. If you are interested, you can see it in Fenix code, but I don't think many of you are going to need that, because most robots have 2 joints and not 3. Okay, so with inverse kinematics you can make your robot move a leg, but how to make it run? Well, any move is just a sequence of single legs moves. Let's take a look how a run sequence looks like from legs perspective. You move two opposite legs up, then forward, then down, then move the body. You repeat that with another pair of legs and move the body again. To move the body, you can simply move the legs, which are standing on the ground, in the opposite direction. So the movement process results in sending desired angles to your servos at the desired pace, and that's it. To control the movements, you are going to need some sort of a control device. Bluetooth joysticks seem to be the most convenient method. You connect the joystick to your microcontroller and implement some action on any button pressed. It is the easiest way to start. It's time to talk a little more about control tools. I've used 3 methods to control the moves of my robot. Connect to robot directly via SSH protocol and use a local commands writer. That's an easy solution if you have a powerful computer running on a Linux-based system. When working with an Arduino, you can use serial port. This method is used only for debugging purposes. Next option is a Bluetooth controller. I'm using a DualShock joystick. It is convenient enough, you've got plenty of different controls and you can program easily any of them. But you're limited to the offered amount of buttons and can't expand it. You can always create your own controller that satisfies your needs. That's not a difficult task if you've already built a robot, but still it takes time. Third option is a web interface. I've got a virtual machine in the cloud and video streaming in real time and can control robot from there. The good thing is that you can put there whatever controls you need, and also you can show data from sensors. Display any information required like CPU temperature and battery's voltage. Another advantage is that you can control your robot from any place in the world via internet. I find it a rather cool feature, but it takes time to program this web interface. The shell. Well, I've got no idea how to make this without a 3D printer, so I can't offer you any other options. Of course you can use wood or metal if you are good at working with these materials, but it will take much more time to create all the required parts, and their weight may become an issue, and it is mostly your manual work. So, back to plastic. You choose some CAD like SolidWorks or Fusion 360, watch some tutorials and start creating your robot parts. I'm using Fusion 360 because it has a free hobbyist version. Then you print them. I'm using PLA plastic for regular parts and Watson for transparent parts to disperse the light. Also my suggestion, always use embedded nuts and threaded inserts, they make your design so much better. And if you want to hide the screws from the viewer, you've got to apply your imagination, because it is not an easy task at all. This is how my robot's legs look like when disassembled. The tarsus part, if you use the insect's terminology, is made replaceable, so I don't have to reprint the whole leg to experiment with it. And if some of your parts become loose, you may think of using a thread locker, but be careful, if the screw is small, you may not be able to unscrew it later. Another very important part, the grip. I've tried many different materials, tried 3D printing with flexible plastic, but found the best grip by accident. I'm using a mouse pad with good rubber. This is how it looks like with and without rubber. You can notice that without grippy parts, robot is just sliding, unable to get body off the ground, because the floor is rather slippery. Overall, this model is too heavy. Total weight is 3.6 kilos. That is too much for this service. Also, this appearance introduces many constraints to the angles of service. That is why this model can't climb any significant obstacle like my previous models. Sensors and periphery. If you want feedback from your robot, you've got to attach sensors. You can measure whatever you want. And you may need some way to find out the measurements results. Common options are LCD screen, indication LEDs, speakers. Fenix has got a front camera, which is a simple Logitech web camera. Current and voltage sensors for each leg. And an IMU, inertial measurement unit, to understand the tilting angle. Current state is displayed via NeoPixel LED strip. It is also used as a flashlight. Most of the standard sensors work via I2C protocol, so if you're choosing some uncommon microcontroller, you should check if it supports I2C, or you'll have to implement it yourself. PCB, which stands for printed circuit board, allows your robot to look nice and tidy rather than a mess of wires. I've ended up using it as a pie head, and I find it the most convenient method. I was using EagleCAD to create this, and I won't show you how to do it because I don't remember it myself. Each time I need to create a new PCB, I go and rewatch a good tutorial. I'll leave a link in the description. Just don't forget one thing, the width of wires must be relevant to the amount of current flowing through them. So if it is a power supply, it should be wide enough. When your PCB design is ready, you can use any online service for printing them. I use GLC PCB, and that's not a paid promotion. If you just connect servos directly to the microcontroller and power supply, you may be able to do that without any soldering. But for more complex projects with several sensors, it will no longer be enough. And anyway, you'd better learn how to solder, that's a must. When choosing wires, you've got to understand the amount of current flowing through them. For a supply wire for a single servo, you need a wire that can pass enough current. For 2.5 amperes, that's a minimum of 0.64 mm and AWG22. For all servos, you're going to need 20 amperes, 2 mm diameter, AWG12. I'll leave a link for this chart in the description. My little advice, use thicker wires for moving parts so they don't get bent and damaged. Also, it is convenient to use connectors like XT60. That is all you need to create your first robot. And it's time to summarize this project. I'm satisfied with this model. It was an interesting experiment, but I wouldn't recommend you to do anything similar, it is too inefficient. I'm going to work on a new, much more efficient model, and work on navigation, overcoming of complex obstacles, computer vision and AI. I've got a LiDAR sensor waiting and I'm looking forward to testing it. My initial idea was of making some sort of a hive mind with centralized control system in a cloud and several robots workers who run around and gather data and evolve. So I will continue working in this direction. If anybody wants to participate in the creation of the visual design of the next robot, feel free to contact me. Well, that's all for today. I hope you've learned something useful. Thank you for watching. That is my first long video, so any comments would be greatly appreciated. If you want details on any of the topics mentioned, let me know. Let's build more robots and help each other, we can make the future brighter.